Okay. Now, so yeah, hi everyone. Course learning. We introduced ourselves. Now, let us introduce the course. So sometimes I stand, sometimes I sit because it's very hard to stand all the time. I didn't know about that the height of this tape desk is adjustable. So last time I was standing for the whole 3 hours, and now I could. Okay, I found out that there is a button here. We can. Yes. Okay. So. Production of the course. This course focuses on various topics in deep learning, covering topics from fundamental concepts in neural networks to state of the art. So from fundamental ones to state of the art. And so we start with neuron and training one neuron, basic learning methods focused on the previous century, the middle of the previous century. Then we cover it. By the way, after preliminaries, so we have some preliminaries and then neuron and training one neuron, including perceptron. Then we cover feed-forward neural networks and backpropagation, and then we cover regularization techniques such as batch normalization and dropout, weight decay, and these things. Then we cover convolutional neural networks, CNN, and some well-known networks such as ResNet, AlexNet, DenseNet, these things. Then you are gonna cover sequence modeling. So it can be useful for NLP, natural language processing, which is text, okay, text processing, and also speech processing. So one of you guys said speech processing, some of you said LSTM, RNN. So these are related. So we are gonna cover RNN, LSTM, attention, which is now state of the art for NLP. Attention mechanism, transformers, BERT, GPT. I think you have heard of ChatGPT. On large language models are nowadays based on GPT and transformers. Okay. Next, generative models will be covered. So variational models, generative moment matching networks, GAN, generative adversarial networks, and diffusion models. So what are these? Let me briefly explain these things. So, for example, in order for you to gain interest in the course, so convolutional networks. What's the short introduction? I'm saying that. Okay, why feed-forward neural network is something like this. I think I can. Something like this. So we reshape the input data to become a vector, and then we feed it to a network, and it will be something like that. It is dense layer. We'll explain them in more details. This is just a short introduction. And then convolutional neural networks say that, okay, well, now consider I have an image, okay? I reshape it, becomes a vectors because image is 2D, right? I have rows and columns. Then I reshape it, it becomes a vector. I feed it to a feed-forward neural network. This is what people used to do for handling images with neural networks, feed-forward neural networks. Can someone tell me what is the problem with this approach?
The image size is like quite large, so the vector that we get from it is like huge. So the computation that is required like increases drastically when it comes to images.
That's good. That's good. That's actually one of the reasons. That's great. Thank you. There's another reason too. There is another issue with that too. So one issue is computational complexities, because you will need a lot of neurons in the first layer, right? For getting the input image, the image as input. What is the other challenge? Reshaping.
So the challenge could be that we have to always convert the image to a vector.
Yeah, and why is it problematic?
Because as he said that in order to create the image to a vector, it might take a lot of time. Same as to when we feed it to the feed-forward neural network.
Yeah, I can say you're right. I think I'm not much worried about its time complexity. I'm more worried that it might not work well because when you have too many neurons in the input, then you can't have too small number of neurons in the next layer. So it increases the number of layers that you have in order to gradually decrease the number of neurons until you become several small number of neurons at the end. Okay, that's one issue. I understand. Although I'm not much worried about its time complexity nowadays, it's very fast to reshape the whole image into a vector. There is another problem, and that's because there is some information between the pixels, like adjacent pixels next to each other, right? When you reshape some image, what happens? Soon I have a 3x3 image, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I reshape it. It becomes 1, 2, 3, 4, 5, 6, etc. Okay. In image, I knew that 2 and 4 are next to 1. So there was some information. Now, when I reshape that, 2 is next to 1. This information is preserved. However, one of the information pieces that we had got lost. And that's the adjacency of 1 and 4. So that's why. So the correlation, the 2D correlation of pixels in image get lost. The information will have some loss of information when we reshape the image. That's the thing. That's why that inspired people to propose convolutional neural networks in order to take the image as it is, not reshape in the reshape format. And some people also improved it. So there are several variants of that, such as AlexNet and ResNet and these things. So about sequence modeling, so we are going to cover. So, and by the way, who here knows about NLP, natural language processing? Raise your hand. I want to know how many. Okay, so thank you. So NLP, natural language processing or text processing. So when you have text, you want your machine learning model to understand it. So there are many different tasks in NLP. One of them is question answering. For example, you ask a question and you want the model to answer you. Some of them are sentiment analysis. You want to understand whether, for example, this is a positive comment or a negative comment. Is this a hateful comment? So I hide it from comment section. For example, YouTube does that. Or is it a good comment? Because we want the machine do that. We don't want to hire people to check all of the comments one by one. It's very hard for people to do that. So in order to automate these things, we need NLP models, natural. Another thing is that you give a part of this text to image and use to your learning model or your neural network, and it will say continue it. This is what kind of ChatGPT does, right? Something like that. So you can say, okay, I have this paragraph, continue this. So based on the style that you have given to it, it will continue that style. So that's one thing. So NLP is for these things, and a lot of companies are actually invested in NLP. Many companies, especially in telecommunications, I don't want to name anything because they will record it. But there are some companies, telecommunication companies in Canada, which are focusing on NLP. Why? Because you'll need it in your cell phone a lot. So that's one thing. Speech processing. Who here knows about speech processing? Yeah, it's less well known, but speech processing is similar to natural language processing because it is both of them are sequences. So text is a sequence of words or letters, right? words or tokens also it's called. Speech processing is a sequence of, I think they call it phonemes. So there are some voices, small pieces of voice, you put them together, becomes some sentence that I'm saying, right? So for speech processing, and I think it has different tasks. I think one of them is understanding the speech. So I say something, I want the machine learning model or the deep neural network to understand that. The models that we are going to cover, they can be used for NLP speech processing, whatever has the essence of a sequence. So it doesn't necessarily need to be NLP in speech. Someone might have some sequence data. And they want to handle it or train it for the neural network, and they need to use sequence model. Can you suggest some other sequence data? One of them is a stock. Yes, stock. One of them is weather data. So whatever is a sequence, because for weather prediction, for example, you have data from last year until now. What is tomorrow? Also, stock. What?
So wireless sensor networks that generate sequence data, for example, for fetching humidity in air or something like that.
Okay.
I think these type of data and application can be a sequence modeling.
That's great. That's great. Thank you. So, in order to be recorded with higher quality, so someone said that it can be used for wireless communication data. You said
Wireless sensor networking.
wireless sensor networks. That's great. Thank you very much. So these are, yes, all sequence-based models. And RNN, recurrent neural network, was one of the first methods to handle sequence models. We'll see it has some recurrence in it. It has some recurrence in it, right? Because as you see, you can say whatever you have, you can go back to, for example, you have a word, it has some relation to its previous word, or it has some relation to its two previous words. So there is some concept of recursion here. LSTM came, long short-term memory networks came, and they outperformed RNN. The idea was simple. RNN said that, okay, I will learn whatever I can, and I stack. So you give me the first word, okay, I will try to learn it. Then the second word, first, after then second, then the third comes. So I'm kind of learning first, second, third. Eventually, they saw that they can't handle all of the accumulating, right? You have some shortage of memory and these things. So they said, okay, let's have a window. The last, for example, 100 ones, something like that. However, then some people said, we consider these two examples. Let me think. Okay, the police is chasing the thief. Okay, the police and thief are very close to each other in this sentence, right? The only words between them is chase and chasing. So for this, we need only short memory. Now consider this example. Let me think. So I was born in France. We had a great time there. I remember I and my family had a great life, and we traveled around the world. It was a great childhood that I had. That's why I can speak French. See, this French is related to the France. As I said at the start, there were a lot of words in between. However, human's mind understands that there is a relation between France and French, but machine also needs to understand that. So we need some long memory. So we need both short memory and long memory. Therefore, they propose short-term memory, long-term memory and short-term memory, LSTM. So that was one thing. And several years ago, some paper came and said that attention is all you need. So they said, okay, let's get rid of recurrence. We don't need recurrence at all. We can replace it with something named attention. And what is attention? When you look at the Mona Lisa picture, focus on its, for example, smile and its lips and its eyes, her eyes, I mean. And then, do you attend or do you notice that, for example, there is a river behind her? There's some stuff behind her. You don't notice those details behind the scene behind Mona Lisa. You attend, you focus on her face, right? So humans' mind, especially humans' eyes, does that. So, for example, or another example, that was for image. You see that our eyes do that. But another example is that when you skim fast reading, you have a page and you have 10 seconds to read it. What do?
Look for keywords.
What?
Sort of look for keywords.
Yeah, exactly. You skim and you just attend to some of the important words, right? So this is a technique for fast reading. You skip a lot of words and you focus on some of them. So that's for NLP part. So in both image processing part and for both and NLP part, in real world, we attend. And what is this attention? If we want to model it mathematically, what is this attention?
Sort of wait, right?
Exactly. We are waiting. So, for example, when we are looking at the Mona Lisa, we are weighting her face more compared to her background. When we are reading the words, we are giving more weights, the important words, and we are just giving. We are skipping many words, meaning that we are not giving any weight to them. So that's why, and I think that's why they called it attention mechanics, because the model is attending, focusing on some things, and it has been used in both NLP and image processing. And transformers were based on attention, so they used attention. So there are transformers are some autoencoders which use attention blocks in them. And BERT and GPT, they are both state-of-the-art methods for NLP. And like I said, as I said, transformers are autoencoders. So an autoencoder we will see these things. This is just introduction. Autoencoders have encoder and decoder. The encoder gets something, encodes it, and then decoder decodes that, constructs it, for example. Okay. And the encoder part, a stack of several encoders of transformer is called BERT. And now I think you can guess GPT. It's a stack of several decoders of transformer. Yes, and they are now competing with each other, BERT and GPT. So these are things like now, generative models. What is generative models? What do? They get some noise. They output something interesting and realistic. Okay. So by you feed some noise to it, but it gives you some realistic data, and you will wonder whether it's real or is it fake. An example is that I think you have seen a lot of faces, facial images, which have been generated and they don't exist on the earth. And that's interesting. So with generative models, we can have different approaches for generative models. One of them is based on variational Bayes. Do you know Bayes model or probabilistic model, I can say. So we will go over these things. It has some preliminaries. I have mentioned some of the preliminaries on probability in the other course, but probably when we reach these points, I will also mention those preliminaries briefly for this course too, in order to jump into variational invariance. So that's one thing. Another one is generative moment matching networks. It says that because so the idea is that it uses moment matching, maximum mean discrepancy, and that's one of the methods in order to calculate the difference of two distributions. So have you heard of tail divergence, for example? If you haven't, don't worry, we will cover these things. So tail divergence says that, for example, in the space, how do you calculate the distance between 2 points? You can simply get the Euclidean distance between these 2 points. Consider a line connecting one point to the other one and just measure its length, okay? But what about the distance or difference of two distributions? Two probability distributions. There are several techniques. One of them is scale divergence. One of them is maximum mean discrepancy. So we will cover these things. And generative moment matching networks are based on that. GANs are based on adversarial learning. So GAN is short for generative adversarial network. And it outperformed variational model. It was proposed by Goodfellow et al., Goodfellow and Benjuan et al. You might have heard of their names. So it's now in Google. So what does it say? It says that, okay, let's consider a game theoretical approach, saying that I have two agents, consider two agents. They want to compete with each other. And because of this competition, they get stronger gradually. So whenever, even in the real world, whenever two people compete with each other, if they competed in a good way, not in a bad way, they both get stronger. So because this wants to get better compared to the other one, studies better or works better, so it improves. The other one also improves, so they gradually improve while they are competing with each other. So this is the idea of GAN. So it says that, okay, I have a classifier which discriminates whether some data is fake or real. Okay. I have a generator also, which generates some data out of noise. Okay. Now I want to see whether this discriminator, this classifier, can identify whether the generated data by the generator is fake or real. So that's why they both get stronger, because this wants to find out whether it's fake. The other one wants to generate realistic data. And as you see, it's a game theoretical approach. Game theory is a field in mathematics. Okay. Also used a lot in economy. So diffusion models nowadays are state of the art. They even have outperformed GAN. If you have seen in LinkedIn, there are a lot of weird things saying that you say, I have seen these posts a lot in LinkedIn. You say, okay, I want a lion sitting on a donut in the ocean, and generate some image for you. And those are generated by diffusion models. And what is that? The idea is that when you have some data, some image, for example, you can gradually add noise to it. When you do that, at the end, it becomes complete noise. Now let's reverse this process. When you reverse it, it becomes a generative model. From the complete noise, it becomes the image. That's one thing. Okay, we also will cover Boltzmann machines, graph neural networks, deep reinforcement learning, meta learning, network compression, federated learning, explainable AI, and self-supervised learning. So let me briefly talk about these things. So Boltzmann machines. Also said that in the other course briefly, but let me explain a bit. So, well, whenever you have some neurons like this, so consider only a two-layer thing, the layer 2 and layer 1. Okay, they are connected to it. Assume they are connected to each other. Get it? Are connected to each other. if they are also connected in the layer 2. Assume each of these layers have some energy, physical energy. Okay, assume. This is called Boltzmann machine. The Boltzmann machine is a machine of 2 layers. There are some nodes or neurons, whatever you call it. And each of these layers have some energy and they can pass energy back and forth. This is called the Boltzmann machine. Now, when we look at it, we'll see that it's not similar to a 1 layer of neural network because we have some connections between the neurons of the same layer, which usually we don't have such cases in neural network. We'll see these things. And this is just a short introduction, okay? So let's get rid of these. In other words, let's restrict it. That's fine. When you restrict it, then when you get rid of these things, it becomes restricted Boltzmann machine, RBM. And RBM, as you see, you can see, consider a fully connected neural network. Every layer can be seen as a restricted Boltzmann machine. So why are they important? If you have heard Hinton's speeches, I think since 2000 to 2005, 6, whatever, until now, even until now, always he talks about Boltzmann machines in his speeches. Hinton is one of the important scholars, Jeffrey Hinton, is one of the important scholars in the area of AI, okay? He was professor in University of Toronto and also working in Google, but he quit Google several days ago. So why is Hinton very interested in Boltzmann machine? First off, because he proposed it, okay? He and some other authors. If you have heard of Max Welling, Max Welling is also an important scholar in AI. He's in Europe. I think Netherlands, I'm not sure, but he's in Europe, okay? Max Welling and many others invested in RBM. And the reason was that we will cover these things, but briefly mentioning, there was some winter for neural networks. And what was that? At the end of the last century and the start of this century, about in the decade of 1990 and 2000, something like that. Kernel SVM got a lot of attention from the researchers, okay? It's basically saying that SVM is a linear classifier. And for handling nonlinearity, they proposed kernel SVM by just increasing the dimensionality of data. And then they applied the linear SVM. So linear SVM plus some kernel notation, it could even classify nonlinear classes. And it was working very well, although it has its own drawbacks, but I'm not going to talk about it here. Because of the kernel SVM, there was some lack of interest in neural networks at that time. There's another reason too. So this, and also they saw that they can't make the neural network deep. So they only could work on shallow neural networks.
Computational issue, right?
Not because, maybe because of computational issue or because that time computers were not as strong, but I think the reason was gradient vanishing. So there is something in gradient vanishing. We will cover these things. So what is this? It says that because as we will see, backpropagation which is the main learning algorithm for neural networks, is just gradient descent and chain rule, okay? Optimization. So when you make neural network very deep, when you start from the last layer and you come by chain rule, you come to the first layer, the gradient might become smaller and smaller because of multiplication. So when you multiply 100 small numbers, it becomes too small. The other way around, it might explode. If you multiply very big numbers, it becomes infinity. So either we have gradient vanishing or gradient explosion. Because of these, they couldn't make it deep. Therefore, they were stuck with shallow neural networks. So to sum up, there was a winter for neural network. Many papers which were working on neural networks got rejected in important conferences such as NeRIPS. At that time, it was called NIPS. So it is a very important conference in machine learning. At that time, they were rejecting almost all of the papers which were working on neural networks. Nowadays, it's the other way around. Most of the papers are on neural networks. So that was the reason. And Hinton et al., who had proposed backpropagation, they said, we need to save neural networks. Because neural networks were like their child, right? So they didn't want to lose that in the AI. They said, okay, let's save it. How do we save it? Said in the, I think, I don't remember the exact date, but in the middle of the previous century, maybe 1970, 80, something like that, they had proposed RBM, restricted Boltzmann machine. They recovered it. They took it from stock and brought it back in 2000, 2006, and that time. They said, okay, let's use the previously proposed RBM in order to save neural networks. Okay, backpropagation didn't work. Well, you will use RBM in order to train neural networks. So that's why, as you see, and again, if you don't believe me, go and watch Hinton's speeches. He usually talks about RBM. I wasn't in the area of AI at around 2006, but my supervisor, Mark Crowley, told me that he remembered, I think at that time he was in UBC. He remembered that Hinton used to go to different universities across Canada and US and giving speeches about RBM. So that's one. And going faster a bit, graph neural networks, they take graphs as inputs so they can handle different lengths of data. Deep reinforcement learning. Reinforcement learning, what is reinforcement learning? Let me briefly also mention that. So assume you wanna, I will cover deep reinforcement learning in another slide that I'm having. So I'm not gonna talk about it, but we're gonna cover that. Meta learning. Meta learning saying that, okay, machine learning says, let's learn something. But meta learning becomes a bit philosophical. Says, let's learn how to learn. Okay, and you can see, according to logic, you have a lot of these. Let's learn how to learn how to learn. Something can go forever. So meta learning does that. That's why it's called meta learning. So and this is also useful for few shot learning. So using a few number of learning points, let's learn the whole thing and generalize well. Network compression. A lot of companies, telecommunication companies especially, they're working on network compression. Why? Because assume you have a huge neural network. You want to have it in your cell phone. It can't. In embedded systems, you need to have a compressed version of neural network. Therefore, you will need network compression. And one of the techniques for that is knowledge distillation. In that, we have two networks. One of them is teacher, and one of them is a student. So the teacher network is a big network, the original network. The student network is the smaller one, the smaller version. And the student tries to mimic or imitate the teacher. In this way, we'll have a smaller version of the bigger network. So this is network compression. Federated learning. What is it saying? It's a distributed learning. Distributed. And what it says that let's have several servers. Okay. And I have a copy of my neural network in each of these servers. And these servers also have their own data sets. Okay, that's fine. These servers have their own data set. So I have some weights of neural network. So I'm in the central server. All of the other servers are connected to me, but they are not connected to each other. So they train for several iterations on their own data. And consider notes that these are the same copies of neural network. Okay, so they train on their data, this train on their data on the other one, and then they give me their weights. I take an average, of these weights and I give them back the average weights. Then they replace their weights with the average weights. They continue the training. So this goes back and forth. As you see, even the central server can't see the data of each of the servers. So it's good for privacy. That's one. And security. Okay. And I think now you can see that industry likes that because they're very private. They don't want to share data. So that's one. That's why many companies are investing in federated learning. So another one is making it distributed. It's a distributed learning. Explainable AI says that, okay, I learned something, I train a neural network, but how do I trust the neural network? There's a paper named why do I trust you? Something like that. Okay. Why do I trust you, neural network? Hey, why do I trust you? Is it a magic? You need to explain to me why is this working. Although the theory of neural network, if you want to see in theory why neural network is working, we know why it is working. So there are several papers. So if people tell you that we don't know why neural networks are working, no, it's not true. We know. There are some theoretical papers which use hack learning and probabilistic probability bounds and all of these things in order to prove why neural network is working in the optimization landscape. So theoretically we know, but ignoring that, when you have some neural network which is trained, I want to know why. Why is it working without the theoretical approach? Okay, so that's where explainable AI comes in, and there is a method, especially in it, named saliency map, which says that okay, assume I have some image, I feed it to the neural network. For example, there is an image of dog and cat. Both dog and cat exist in this image. I give to the network, and it gives me, for example, assume that in the training phase, I have said that this image is a dog image because the dog was bigger and the cat was small, for example. Now, after training, I want to see what has it learned. So saliency maps takes derivative of the output with respect to the pixels of this image in order to see which pixel or which pixels have played more important role in the decision. And you will see when you do that, you will see that it is focusing or it is looking at the dog space rather than the cat space. If you do the other way around, if you say to the network that this is a cat, it will focus on the cat. It will ignore the dog. Now you can see that you can visualize by weighting the pixels, saying that, see, now you can trust the neural network because it is understanding that this is actually a cat thing or this is a dog thing. So it explains why it is working. Self-supervised learning, it says that, okay, so we will talk about supervised and unsupervised thing, but briefly talking about what self-supervised learning is saying that in supervised learning, we need labels. I will tell you what label is in a few slides. And unsupervised learning doesn't have labels. So self-supervised learning says that let the machine learning model itself generate its label. Something like that. Okay. That's why it's it itself makes the labels. So that's the thing. And also some applications, computer vision image processing, NLP, if time allows, we will cover the theory of optimization in neural networks, the probability bounds and these things. And probably we'll also cover, if time allows, also cover adversarial attack. Okay, let me tell you what these are. So we have two use cases of adversarial in machine learning. One of them is adversarial learning. The other one is adversarial attack or adversarial defense. What are these? So adversarial learning, I already explained in GAN. Remember, I said two things compete with each other adversarially, right? The other one is adversarial attack, saying that, okay, assume I have horse. And I have trained my neural network on the images of different animals. And then I have a horse image. I give to the network, it says this is horse. This is correct. Now adversarial attack techniques try to find some pixels with fewest amount of change. It changes some of the pixels or some parts of the data that visually I can't understand. So after this change, when I look at the image, I'll say this is horse. Maybe 2 or 3 pixels have changed. Then after this change, we feed that to the network. It gives us that this is a camel. It completely confuses the network in an adversarial way. This is an adversarial attack. And as you see, it has some security things, related things. So now there are some techniques named adversarial defense in order to defend to these attacks, saying that how can I make my neural network robust to these kinds of attacks? Okay. We have some tentative schedule of weeks, but I'm not restricted to finishing something in the same week. So, but this is tentative. Course materials. Lecture notes will be provided to you, and we'll have a YouTube channel. Feel free to subscribe to that channel. I will upload videos of both statistical machine learning course and deep learning course to that channel for you to review the courses if you want. You have that. Also, there are some tutorial papers that we have written. I think they are useful to read, not mandatory useful to read, but I think the lectures will be self-explanatory. Additional resource for interested students, Professor Ali Qotsi's lectures at the University of Waterloo. He has a YouTube channel. Just search Ali Qotsi, it comes. Okay. His courses are very good. Also, Carnegie Mellon University Deep Learning, that's also a good YouTube channel focusing on deep learning. There are other channels too, not only these two. Also, some additional books. I think some of them can be found in the library of the university too. So one of them is Elements of Dimensional Reduction and Manifold Learning by Springer. It is our book. We have written that recently published. There is another one, which is the most famous one, Deep Learning by MIT Press by Goodfellow, Bengu et al. There is also an upcoming book, which is, I think, very good, Understanding Deep Learning, which is going to be published by MIT Press. It's by Prince. Prince is a famous scholar in both machine learning and computer vision. So also there is pattern recognition and machine learning by Bishop, Springer. I think that's also good, especially the variational invariance things. Bishop is good. And some research articles in the literature. So introducing me and the TA instructor, I'm Benjamin. This is my email address. And also the TA is Sepide Emami Tabrizi. This is her email address. Feel free to contact her if you would like. So courses will be in person and discussion chats will be in the Microsoft Teams group. I don't know why not everyone has joined the group. Please join the Teams group. I have put the link in the course link. And please note that you're responsible to regularly check your course link. I make announcements there. So, okay. So feel free to join that group. And if you have any question after the class, in the class you can ask. After class you can ask there. And whenever you ask question, please tag or mention both me and the TA, because Teams doesn't notify well. Yeah. So if you don't tag me and the TA, you might not even understand, find out that you have asked a question. Okay. So the courses there is also a website for homepage. For the course, although I updated it slowly, so course link is updated often, but this is done slowly. I will probably upload, yeah, I will put the videos on YouTube and I will exclude the personal information of the student. So, by the way, before continuing that, don't look at me as a professor or something. I'm your friend. Consider me as your friend. And we are all gathering together. And it's in order to learn deep learning, and in the other course, in order to learn statistical machine learning. The only difference is that I'm sitting here. So, no difference. And feel free to call me Ben, Benjamin, Benjamin, whatever. We are some, if, whenever you have question, you don't need to raise your hand, just interrupt me, ask, okay? Yeah, this is a discussion-based thing. And I don't hold your questions because we build up. If you don't understand some parts, maybe later you'll have problem understanding. Please ask your questions. And if I don't know anything, I will not lie. I will say I don't know. I will go and check it. I will come back next session. I'll sit. I might make mistakes. Please correct me if I find out that I'm making a mistake. Also, this field is big. So if I don't know anything, let me know. I will go read it and I will come back. So for example, you say, okay, this is also interesting. Will you cover that? If I have time and I can do that, I will go read it and we'll cover it. So these things, yeah. And we will try to cover both fundamental and state-of-the-art things. Okay. So about the course evaluation, assignments 20%, and they will be posted on course link along with the due dates or individually. We have several, maybe 2 or 3. I'm not sure how many, but we'll see how many we can have assignments. The midterm exam somewhere in the middle of the term. Note that we don't have any summer break. The summer semester is short, therefore there is no reading week. That's one thing. And details will be discussed in the class. Course project 40%. So we'll have a course project and also its presentation. So we'll have teams. We'll figure out the number of people in each team later. And then you will work on the project at the end of the semester. At the last lecture of the semester, you will present and you will hear the feedback, and you have several days or maybe 10 days to apply your the feedback on that and write a report and submit it. Submit the report and code, all of these things. So in the middle of the semester, we'll ask you to send us the proposals as well as the team members. So proposal doesn't have any grade. We just want to check whether it's good or not, something like that. And group presentation, you will present. Bonus points, this is important, participation in class and discussions and ask questions. This is very important. I said that in the other course too. I don't want to be the sole speaker, okay? This is the approach of teaching which I hate. I want us to all learn together. Ask me, oh wait, I mean, by the way, this, whatever it is, I have another opinion. Challenge me, okay? And let's have discussions. And don't worry much about your marks. For those of you who were not in the other course, so this is my approach of teaching. Twofold. One thing, I try to teach with high quality, at least in my opinion. So it might have some theory too, but you don't need to be afraid. Why? Because the second fold is that I take it easy in assessment. Okay. And why? Philosophy is that because the reason of the courses is not for passing or for grades. It's just for learning. Exactly see this course as you are watching YouTube. Okay, you're watching YouTube and learning. When you watch the YouTube courses of Stanford or MIT, do you care about grade? No, you don't. So So the same here, but it doesn't mean that you shouldn't do your best. Do your best. Do your best. Don't say that I don't do things. I don't do your best. Do the assignments and the midterm and the project completely. But don't worry about the marks. Okay. And when you see theory, don't be afraid. The theory is for you to understand it. Focus on understanding, and our goal is for both industry and academia. Okay? For both practice and theory. So as much as I can, depends on how much I can have time and energy and these things. I'll try to also cover some code and these things. So we'll have code and theory both together. The programming language will be the main programming language will be Python. The libraries will be PyTorch and TensorFlow. But I think our focus will be more on PyTorch because TensorFlow is a pain in the neck. That's one thing. But we might have, so depending on the subject, see which one is easier. At least several years ago, it was like this, that image processing things were easier with TensorFlow, and I think, and NLP things were easier with PyTorch. Nowadays, I think everything is easier with PyTorch. We should see. So that's one thing. I think you know the reason, what? PyTorch is developed by Facebook, and Facebook was focusing on NLP things at that time. But Google, TensorFlow was by Google, and Google was focusing on image processing. So that's the reason. About theory and practice, we will learn some theory and also code in practice if it is possible. And ask questions. I don't want to be the sole speaker. So, okay, we'll have breaks. So let's have a break and maybe let's come back at 8:25. Is it good? 8:25, I think is good. Okay, great. So we'll have breaks. We'll have breaks, by the way, and we usually stay until the end. So don't complain about these things because we want to cover things as much as possible. But we'll have all these breaks in the middle, about 15 minutes. Okay, 8:25. I think. Thank you very much. We continue now. Okay, preliminaries, and we need yes. So let me go a bit fast. So the first part of this preliminaries were already talked about in the statistical machine learning course. However, I need to repeat this for those who only have this course. Okay. So first off, let's talk about data set. So machine learning models, including deep learning models, they work with data set. And what is that? Consider the measurement of a quantity. This quantity can be anything, personal health data, including blood pressure, blood sugar, blood fat, or images from a specific scene, but taken from different perspectives. Or images of several categories of animals, such as cat, dog, frog, etc. Medical images, such as digital pathology images, also called histopathology images, or including healthy and tumorous tissues or biomedical applications, or any other measured signal. Consider some quantity of these measurements. The quantity can be multidimensional. That is a set of values. For example, if you have a health data and you have a value for blood pressure and another value for blood sugar, for blood fat, and these things. So it can be multidimensional or set of values. Therefore, every quantity can be considered as a multidimensional data point in the Euclidean space. So you can see it as a vector, and this vector can be seen as a data point in the multidimensional Euclidean space. Let the dimensionality of this space be d-dimensional, meaning that every quantity is a d-dimensional vector or data point in RD. When I say RD, it means that it stands for real, because you usually work with real data rather than complex data. Right? And when we say RD, it means that a vector of d-dimension, dimensional vector in the Euclidean space. Okay. The set of d values for the quantity can be called the features of this quantity of the vector. So every vector has some features, right? Multiple, by the way, ask me questions if you have any. So multiple measurements of the quantity can exist, each of which, so for example, we have blood pressure of Jack, John, Jennifer, and these things. So we have several people's, several measurements, multiple measurements of the quantity can exist, each of which is a d-dimensional data point. Therefore, there will be a set of d-dimensional data points, and we call it data set. Okay. So we have a set of vectors, and we have them, and we call it data set because it's a set of data. For example, the quantity can be an image whose features are its pixels, right? So we can see every data point as an image whose features are its pixels. Data set can be a set of images from a specific scene, but with different perspectives. Now, so this is data set. And you usually work with data set in machine learning. Now the learning model. Now that we know what data set is, consider a data set of n data points, and xi, it means that the ith data point, and it is the d-dimensional vector. We have set of them. I goes from 1 to n. Each of which is a d-dimensional vector in the Euclidean d-dimensional Euclidean space. We can put these vectors column-wise in a matrix X. So first off, when I say small case not bold, it's a scalar usually. When I say small case bold, it's a vector usually. When I say capital case bold, it's a matrix. When I say capital case not bold, it's a random variable usually. By default, I'm saying it. These are my notations. Okay. And when I say fancy letter, capital case is a set. So again, small case not bold scalar, small case bold vector, capital case bold matrix, capital case not bold random variable, capital case fancy set. And so what consider each, by the way, usually vectors by default are column vectors. When I say RD vector, it means RD by 1. Okay. And when you put them next to each other in a column, column-wise in a matrix, it becomes a matrix X in RD by n. What does it mean? In real Euclidean space, E rows, n columns. Okay. And you can see it as a outer product of RD and Rn. Okay. Rows and columns, D rows and n columns. So this is notation. Now consider a learning model F, which is a map. Map or mapping is a concept in mathematics, which maps something to another thing, from one space to another space. Function is the special case of map, right? Because in function, you can't have two outputs for the same input. So consider a learning model F, which is a map from data space to some output space. And we draw it in this way. F goes from RD to RP. So D is a dimensionality of data, P is a dimensionality of output. P might be 1. We can also see it as a map from X to F of X. Right? Usually, not always. Usually P is less than or equal to D, but not necessarily. And you can see this model as this. So you have some data set for data. This is a model F. You will get F of X. And for your own task, such as classification, regression, whatever, which we will cover, you will learn this F. So these F's have some parameters, and we need to tune these parameters in order to do what we want. So the output is what satisfies our criteria. Okay. This is learning model. Now the whole thing which machine learning and deep learning do is just learning this F parameters of. Learning model is like a newborn baby. it first knows nothing, and we should teach it. Consider a baby. Baby knows nothing. Now, I'm gonna explain different tasks using the example of baby, for example. So, first off, the difference between supervised and unsupervised. In supervised, let me first talk about classification. Consider you have some, I will say this a bit fast because many of you who already were in the other course already have heard it. So consider some apples and cucumbers, okay? I have a newborn baby, doesn't know anything. I want to teach it what apple is and what is cucumber. So I buy 100 apples, I buy 100 different cucumbers. I show the baby, this is apple, this is another apple, this is another apple. I say to it, this is apple, this is apple. Also cucumber, this is cucumber, this is a cucumber, this is a cucumber, right? So after that, the baby learns what is cucumber, what is apple, because I have shown it 100 apples and 100 cucumbers. Now, when I show the baby an orange after this training, I'll say, what is it? The baby will say, this is apple, right? Because the baby's bowl is only cucumber and apple. There's no orange in its bowl. However, if I show 100 oranges to the baby, in other words, I add a new class to the world of the baby, then the baby can discriminate apples from oranges. Okay. Likewise, if I show a carrot to the baby, it will say it's a cucumber. So this is called classification. The baby is classifying the classes, and I'm also showing the baby the names. These names are called labels in machine learning. So this is cucumber, this is apple, right? I'm saying that this is label. So this is classification. Consider another example. Same baby, knows nothing. I buy 100 apples and 100 cucumbers. Now this time, I put them in front of the baby. I'll say, the baby, I respect your understanding. I will not tell you what is cucumber, what is apple. You, based on your own understanding, try to discriminate them. So the baby will look at them, find out that there is a difference between their patterns. Some of them are round, some of them are lengthy. So it puts the lengthy ones next to each other and the round ones next to each other, right? After doing that, I will ask the baby, what is the name of this? It will say, I don't know, and I don't care. What is the name of the other one? I don't know. I don't care. I may name it table. I may name it refrigerator. I don't care. Right? So there is no name, although they are separate. This is called clustering. No label. And as you see, you are trusting the understanding of baby. You are trusting the understanding of machine learning model. Okay. This is clustering. As you see, both of them the output are some classes or some clusters. But the difference is that in classification, these labels are introduced in the training phase. In the clustering, they are not introduced, and we don't care about these names. We just want them to be discriminated. L1 can be table or refrigerator, whatever. But in the classification, we care that this is L1. This is one thing. Now, regression. So we talked about classification, clustering, regression. Assume I want to have an artificial leg. So assume my leg is cut and I will have an artificial leg. I will bring someone with a healthy leg. I will measure the EMG signals, the signals of the muscle. And then I will say, for different EMG signals, I will say, what is the angle of the knee of that person? I will have a lookup table. Then I will learn these by a machine learning model. I will apply it to my artificial leg, and it will find out, but based on my EMG signals, what the angle should be. However, you might be wondering, what's the point of this? The machine learning, this model just memorized the table? No, it didn't memorize. The good thing about this is that this artificial leg, now this machine learning model, can interpolate and extrapolate this table. So for example, in the training phase, I showed it 80 degrees and 90 degrees. EMG signal for 80 degrees, EMG signal for 90 degrees, etc. There is no 85 in the training. But in the test, some EMG signal comes, which is between the EMG signal of 80 and 90. It could interpolate that. Now it outputs 85. Right? So this is the good thing about it. Otherwise, it would be just memorizing the lookup table. That's called regression. That's called regression. It can be used for stock prediction, weather prediction, distance. Weather prediction is regression. And you might be wondering that it seems that classification can be seen as a special case of regression. Regression output is continuous. It's a range. However, classification's output is discrete. So as you see in both classification and regression, we have labels. As in clustering, we don't have labels during training. Then when we have labels, it's called supervised. When we don't have labels, it's called unsupervised. Reinforcement learning. So it says that assume I want to train a dog. That time I said an example. This time, let it be another example. I want to train the dog to sit whenever I say sit. Okay. So reinforcement learning is exactly like your machine learning model is like a dog. Doesn't know anything. You want to train it, and you use that approach in order to train your machine learning model. What do you say? You say, so you have some environment, some world, and this involved, for example, is the room, and and also my voice, and all of these can make the world of this machine learning model or this dog. There's also a state, whether I say sit or I don't say sit, or I say some other word. This is a state. Also, I have some reward. I have some food for the dog. Whether I have positive reward or negative reward. Positive reward, I give the food to the dog, or I don't give it. Negative reward. So when first time I say sit, the dog does something randomly. My dog here, you can see it as a machine learning model, does something randomly. Jumps, for example. I don't give it the food. So by hunger or negative reward, it learns that it shouldn't jump. Or I say sit. Next time, randomly it sits and I give the food. So it learns the pattern. It learns the pattern by positive and negative rewards. So this is the idea of reinforcement learning. They have used that for training machine learning models in order to play especially games. You can see Atari games, the world and environments. And gradually, initially, the reinforcement learning model tries random stuff, but gradually, by rewards, it will learn how to play. And after a while, after many iterations, it can even outperform humans. Okay? In chess, in Go game, in Atari games, they all have used reinforcement learning. Dimensionality reduction, manifold learning. It's learning an M within a space. So do you remember I said learning model is a mapping. Even in those cases, these were mappings, right? This is the output of mapping. Classification, regression, and all of them, clustering. Now consider the mapping to be a vector, a space, a p-dimensional vector. So it maps from the d-dimensional space to a p-dimensional space. However, in dimensionality reduction, p is always less than or equal to d. And usually p is much less than d, much less than. So it means that we want to reduce the dimensionality of data. Okay. We want to reduce the dimensionality of data. There are many algorithms. Why do we do that? Why do we do it? What's the point of doing this? The point of doing this is this. Whenever you have some machine learning model like this, either as a pre-processing, because raw data is usually hard to process, raw data, especially in industry. It's very hard to process. So what do? Either you do a pre-processing thing. For example, the classes are very confused with each other. You do a pre-processing to separate the classes, and then you feed it to your classifier. So it improves the performance of a classifier. Because if you feed the confused classes to the classifier, its accuracy will be awful. So you separate the classes by pre-processing, but you have to be able to do this on the test phase too. Otherwise, it's useless, right? So you do something on the training phase. You know that you can do it on the test phase too. Then you feed it to the machine learning model. It improves your performance, okay? Either you do this or your machine learning model does it itself in the middle of it. For example, neural networks do that. Neural networks, in the middle of them, they do dimensionality reduction. How? I will tell you. In neural networks, it's considered a fully connected neural network. In neural networks, either you go from a larger number of neurons to a smaller number of neurons, or you go from a smaller number of neurons to larger number of neurons. Two cases, right? When you go from larger number of neurons to a smaller number of neurons, it's dimensionality reduction. You're extracting some features. Whenever you go from a smaller number of neurons to larger number of neurons, it's kernelizing. You are using kernels. Kernels are used for increasing dimensionality of data in machine learning. For example, kernel SVM does that. So as you see, neural network is a stack of different methods in machine learning. Dimensionality reduction, kernelization, dimensionality reduction, kernelization. And because of all of these, it has become very powerful. And that's why there is a quote by LeCun saying that almost all machine learning is representation learning. Representation learning is another name for dimensionality reduction. So we have either unsupervised or supervised things. Unsupervised dimensionality reduction says that I don't have labels, but I want similar things to be closer to each other in the embedded space. There are two things which are similar, but I want to put them closer to each other. And dissimilar things be away from each other, dissimilar patterns. Supervised dimensionality reduction, however, says that now I have class labels. I want to decrease the intra-class variances, collapse each class to 1 point almost, and increase the inter-class variances. So I want to separate the classes better. So I increase the distances between classes. Also within every class, I decrease the distances. So this is the idea of Fisher. Fisher was the first person who proposed the idea. Okay. For more information, you can see the text. Numerosity processing, very fast I go. So there are things like outlier detection or anomaly detection. It says that I have some data distribution and there's something outside of this distribution. Either we want to detect this outlier for the sake of finding, for example, fraud detection, or it is ruining the performance of our machine learning model. Let's find that and remove it. Prototype selection is almost the opposite of anomaly detection. Let's find the best, most important points in the data. Prototype generation says that in addition to finding the most important points, let's generate some important points too. There are some surveys on them. You can take a look at them. Also, for more information, you can see my PhD thesis. I have talked about this. Some other areas of AI, soft computing. Soft computing, sometimes also called computational intelligence. It has fuzzy logic. It's not machine learning, but it's a part of AI. All AI includes machine learning, but machine learning doesn't include the whole AI. So the fuzzy logic and fuzzy control, it says that rather than having binary logic, 0 and 1, let's have a range. Okay, let's have a range. How am I feeling? I'm 70% good, 30% bad, something like that. Heuristic optimization and intelligent search. For more information, you can see my previous course, but roughly speaking, it's saying that when the cost function is too complicated to handle, when you have too many constraints, or when you are lazy, do classical optimization. One of these cases, you do meta-heuristic optimization. It's better than brute force search because of time complexity, grid search. It's better than that. Also, it's an intelligent way. And so it's better than random search. Okay. Biological inspired or third generation neural networks. This is a category of neural networks. Unfortunately, my knowledge on this is limited. Otherwise, I would probably include that in the course. If I can read it and understand it until the end of the semester, I may include that. So whatever we learn usually is the second generation of neural networks. And that has dominated AI. But there is a third generation, and only a few labs in the whole world are working on it. And they are saying that let's go back to imitation of biological neurons. So we started neural networks by trying to imitate biological neurons, but we deviated and we became a lot of computer sciencey. Okay. Now it's very mathematical and computer science, but some people say, let's go back and become more biological. Yeah. And that's called, example is spiking neural network. Because in biology, they spike, they have the spikes of things. So that's one thing. It's the relation to neuroscience and cognitive science. Feature engineering as a pre-processing, it can be divided into feature selection and feature extraction. Feature extraction is the dimensionality reduction, which I explained. The difference between these two is that in feature selection, when you have some data points, in both of them, you want to reduce the number of features, okay? But in feature selection, you select a subset of your features for your own task, For example, for improving the accuracy of classification. Some features might not be useful. Let's get rid of them, right? Or some features might be correlated with each other. So one of them is repetitive. Let's get rid of them. Feature selection selects a subset of features. Feature extraction says, no, let's completely generate a completely new set of features. However, the number of features should be less. That's called dimensionality reduction. Okay. And for more information, I have a tutorial on that. The survey and tutorial on feature selection and feature extraction. You can see that. Application of AI also in various fields of science and technology can be considered as some fields of AI. Now that was a brief introduction to AI and machine learning. Now let's briefly talk about things which are required. Some of things you might be wondering why they are in both courses. I have excluded probability from the preliminaries of deep learning because statistical machine learning has more, requires that more. And many of you have the both of the courses. However, I think whenever we reach variational inference, we might review some parts of the probability too. But some other things are shared in the two things and they're used in both of them. I briefly mentioned them. So linear projection, why is it required for deep learning? Because every layer of neural network is a linear projection before activation function. Activation function, which we'll define, is the only non-linearity. So we have linear projection, non-linearity, linear projection, non-linearity. If you remove these non-linear activation function, the whole network collapses to become one layer of neural network, which is linear projection. And it cannot handle nonlinear data. The reason that neural network is able to handle nonlinearity in the pattern of data is the nonlinear activation functions. Okay, so let's talk about that. First off, column space. Consider P basis vectors. Okay, so by the way, using two basis vectors, we can define a plane, right? A 2D space. Because every point or every vector in this 2D space can be represented as a linear combination of these two vectors. In 3D also, we need three bases, X, Y, Z, right? So what in a p-dimensional space, Euclidean space, we need p basis vectors. So far clear? Okay. Now we can define a p-dimensional Euclidean space by these p basis vectors. Okay. For example, two vectors define a plane, three vectors define a 3D space. In terminology, the P basis vectors span the P-dimensional Euclidean space. This is terminology. So X, Y, Z here, they span this space. What does it mean? It means that the space, every point in this space can, or every vector in this space can be seen as a linear combination of these vectors. This means this. Also, note that every point in the space is what? Is a vector. Exactly. Consider, first off, before that, I should need to say this. Every space, Euclidean space, has origin in it. Why? Because every vector minus itself should be in the space. Therefore, every vector minus itself becomes 0, 0, 0, 0, 0. The origin needs to be in the space by definition. Okay. Consider, assume that this point is the origin in the space. I have a point here, my finger. This is a point, but it can be seen as a vector connecting the origin to this. Every point can be seen as a vector. This, and this. Three components, okay? And so every point or every vector can be considered as a linear combination of these three vectors or these P vectors. And these P vectors span the Euclidean space, or the P-dimensional Euclidean space is spanned by the P vectors. Either the vectors span the space or the space is spanned by the vectors, right? Consider P vectors U1 to UP. Okay. And let each of them be d-dimensional. So we have P vectors, each of which is d-dimensional. Okay. These vectors can be stacked column-wise, put next to each other, to have a matrix U. And this matrix will be D by P. Why? Because we have P columns, P vectors, each of which is d-dimensional. D by P. Now, I'm defining these, I'm building up. The space spanned by the columns of matrix U, so columns of matrix U, the space spanned by these is called the column space of matrix U. Again, the space whose basis vectors are the columns of the matrix U, or the space spanned by the columns of matrix U. Clear? Is called column space of U. And write it in this way. It simply, in simple words, it means that you have P vectors. These define a space. Put these vectors next to each other column-wise. That space is called the column space of this matrix that we just formed. Right? Any question or ambiguity? I want everything to be clear. If you didn't understand, ask me. That's fine. Okay. In other words, the space whose bases are the columns of matrix U is called the column space of matrix U. Right? And this space is p-dimensional because we have P columns, P bases. Right? This slide talked about column space. Now, let's talk about linear projection. Assume there is a data point, X, d-dimensional data point. The aim is to project this data point onto the vector space spanned by the P vectors U1 to UP. So consider you have U1 to UP. They define a space, a P-dimensional space. You have a point, D-dimensional point, P-dimensional space. You want to project this D-dimensional point onto this D-dimensional space. An example is this figure. In 2D, x1, x2, you have a two-dimensional point, right? X here. You have a two-dimensional point. Assume E is 1. This column space is one-dimensional. This is a column space, okay? So are clear? So D is 2 here, P is 1. By projection, I mean that would make a line, connecting line orthogonal to this space. to this connecting line to this orthogonal. You see? This is orthogonal. Right? Now this point. This is the origin, right? The origin for both the two-dimensional space and the one-dimensional column space, right? Do you agree? After this projection, I don't care about the two-dimensional anymore. After this projection, it becomes one dimension. Now on this one. So I can get rid of these two. I can show it as one line. This was the origin. 0, 0, 0, 0. This was here. This was here, right? And this was the projected point. I denoted by x tilde. This length is x tilde, one dimensional. So I projected a two-dimensional vector onto a one-dimensional space. Its distance from the origin is one scale. This is x tilde. Okay. This is projection. However, I can reconstruct it. What do I mean by reconstruction? Now let's go back to the 2D. This point that I'm pointing at, this point, this is projected point if you only consider this. Now, where is it in the two-dimensional space again? See, after projection, you can see it in the two-dimensional space again. Although it's not the original two-dimensional space anymore, it's two-dimensional point anymore. That is projected. Clear? Okay, so if I see it again in the two-dimensional space, it's reconstructed, denoted by x hat. X tilde, x hat. You should understand the difference between x tilde and x hat. X is d-dimensional. X tilde is p-dimensional. X hat is d-dimensional again. You get it? Yeah. I think you got confused. So x is d-dimensional. X is d-dimensional. X tilde, which is projected point, is p-dimensional. If I see it in the d-dimensional space again, x hat is d-dimensional again. Okay. So now that we have understood the concept, let's go into the mathematics of it. So, by the way, usually p is less than d. Why? Because we usually want to project onto a subspace. When we say, why do you call it subspace? Sub means that less, right? It has less number of dimensions. Usually, not always, okay? So these vectors can be stacked, the U vectors can be stacked together to become U matrix, P by P. In other words, the goal is to project X onto the column space of U denoted by this, right? We defined that in the previous slide. As P is less than D, this projection is projection onto a subspace because we are projecting from D-dimensional space onto a lower dimensional space. The projection of X D-dimensional onto this column space, which is P-dimensional, is this. And I tell you why. This X is D by 1, right? It's the column vector, D by 1. U was D by P. So U transpose is what? P by D. The whole thing becomes P by 1. That's what. Beautiful. So it became P-dimensional, right? Now, I want to make it D-dimensional again. I need to use U again. How? So, X tilde is P by 1, right? U is D by P. So the whole thing becomes D by 1. X tilde, I can replace it from equation 3. Transpose X. So U X tilde, which is U transpose X, is reconstructed data. So U transpose X projects data, U transpose X reconstructs. Reconstruction is its representation in RD again, but after projection. After projection. Therefore, there is always some reconstruction error, some residual. So there, as you see here, there's a distance between them, between x and x hat. You might be wondering, why don't we? So here, this is the definition: x minus x hat. Why don't we say x minus x tilde?
X has
Nonsense mathematically. X is d-dimensional, x tilde is p-dimensional. How can you subtract them? Okay. You need to have x hats again to become d-dimensional. So now we can subtract them. Okay. You can see it. So reconstruct, there's always residual or error. So you can see it in this way mathematically. Consider this is a column space. I'm projecting x onto this column space and then seeing it again in d-dimensional space. And there is some residual error between them. Okay. By the way, if the data point is already in the column space, what happens? The residual is 0. An example. This is column space. The point is here. Point is here. This projection is equal. When you project it, it becomes this. When you reconstruct it in the 2D, it becomes this again. Okay. Now let's talk about norm. So by the way, you'll need norm a lot in machine learning and deep learning. DOS functions have a lot of norms in them. Okay. Definition. Inner product of vectors. Let's talk about inner product. So consider two vectors, x from x1 to xd. Why do I say this is transpose? Why do I have transpose here? Because I want it to be column vector. By default, my vectors are column vector. And why? D-dimensional, y1 to yd. The inner product, also called dot product, is defined as this. We can either say x transpose y or y transpose x equivalent. And we can denote it by this. Also, it's just saying that x1, y1 plus x2, y2 plus until xd, yd. You can write it in the summation form. This is inner product. Easy. That was inner product between vectors. We can have inner product between matrices. We also have inner product between matrices d by 1, d by d2, x and y. Let xij denote the ijth element of matrix x. Right? Then what happens? The inner product of x and y is defined, you can see it as this. But you need trace. What is trace? What is trace? You can see it in two ways. The main definition of trace is this that I'm telling you. Trace of a matrix is defined as summation of its eigenvalues. What are eigenvalues? I will define it in a few slides. Just give me some time, okay? The trace of a matrix, summation of its eigenvalues. That's why, as far as I remember, if I'm not wrong, the input of trace is a square matrix. If I'm not wrong, you can check it up. Look it up. If I'm wrong, please let me know. The trace of the input of trace is a square matrix, n by n, d by d, cannot be d by n. If I'm not wrong. Also, there is a side definition of trace that's saying that it's addition of its main diagonal. So it can be mathematically proved that if you sum the main diagonal elements of the diagonal matrix, it is equivalent to its summation of eigenvalues. So it is equivalent to its trace. Okay. That's trace. Two definitions are provided for that. Why do I need trace for inner products of matrices? Why do I need that? For vectors, we didn't have any trace. Because output of inner product should be a scalar. X transpose y when it is matrix is a matrix again. It's not a scalar. I have to make it scalar. So I need to have the trace operator. Output of trace is scalar. It can be seen as this. This you multiply the elements of the two matrices. Okay. Similar to we had this for vectors, but now it is for matrices. You multiply the elements, the pairwise elements of the two matrices. This is inner product of matrices. Now, norm, because norm requires inner product in its definition. The function norm, we denote it in this way from RD to R. So it means that the output of norm is a scalar. If you see it as this map, is a norm if it satisfies four things. First off, it's for all x, always non-negative. Can be zero, can be positive, cannot be negative. Another thing, assume A is a scalar. For all x, when you have this, you can bring A out of the norm. So in the multiplication, you can bring A out of the norm, but it should you need to take absolute value. Because norm is non-negative. That's because of the property one, you have to have an absolute value. We have if and only if here, two-sided. If norm is zero, its input is zero. If its input is zero, norm is zero. Two-sided, right? The last one, which is the most interesting one, triangle inequality. The norm of x plus y is less than or equal to norm of x plus norm of y. An example. Already have said this example to people in the previous course too, in the optimization. I have a donkey here. I have some food here. Paths. Okay. Either the donkey can go from A to B to C, or from A to C. Which one will the donkey choose? A to C. Why?
Sum of two sides is always greater than the sum.
Yes, AC is shorter. Because even the donkey understands that this is a shorter path. I don't need to go to B and then go to C. That's why triangle inequality, its other name in Persian or Arabic is Ghaziyatul Himar, which means the principle of donkey. That's the reason. Okay, so I think by this example, you understand this completely. It's a triangle inequality. Needs to satisfy this. By the way, the definition, if you take a look at definition of distance metric, that's very similar definition to this. Why? Because you can see a distance as a norm. I tell you why. When you say norm of x, you usually mean the length of x, okay? So we have different measurements of the length. L2 norm, L1 norm, whatever, we'll see. But it's a measurement of length. It means that in the space, in whatever dimensional space that you have, this is the point x or the vector x. Connect the vector origin to this point. The length of this, with whatever measurement that you have, either L2, L1, whatever, is the norm of x. Now, let's talk about distance of two vectors. The same space. What is the distance? It's just the length of this. So you can see this as norm of x minus y. Why? If I'm not wrong, this is x, this is y. X minus y is a vector connecting y to x, right? I think I'm right. Right? So this is the vector x, this is the vector y, this is x minus y. And we know that the distance of x and y is exactly length of this. So you can see it as the normal minus y. That's why you see the connection between distance and norm, because you can see distance as norm of something minus the other one. Important norms
for vectors. Some important norms for a vector X are as follows. LP norm. I think the most important norm that you need to know in these things are LP norm. There are some other complicated norms too, but maybe out of the scope of this course. But if we have time, we can go over them too, such as nuclear norm and these things. But for now, let's talk about LP norm. LP norm is defined as this. So you will take absolute value of elements, x1 to x2. You to the power of p, you sum them, and then the whole thing to the power of 1 over p. We can see it as these two, the pth root. Right? You see it as this. Where p is greater than or equal to 1, this denotes the absolute value. Two well-known LP norms are L1 norm and L2 norm. L2 norm is also called Euclidean norm. Euclidean norm. With L1 norm, P is 1. In L2 norm, P is 2. Okay. And that's it. So in L1 norm, you will have set P to 1 in this equation. You will have this summation of absolute values of the elements. L1 norm. L2 norm is second root of summation of a squared elements. As it is a squared, I can get rid of the absolute value. Okay. Did you understand it? Now, important norms for matrices. Matrices also have norms. The most important one I can, at least in our application for now, is Frobenius norm. Consider the matrix D1 by D2. The formulation of the Frobenius norm. Frobenius was a mathematician. For a matrix is similar to the formulation of L2 norm for vectors. By the way, don't confuse that. We have L2 norm for matrices too. I'm not talking about it here. You can see, I think it's mostly used in pure math. I'm not talking about that. Although, ignoring that, formulation of Frobenius norm is similar to the formulation of L2 norm for vectors. Consider these. In L2 norm for vectors is this summation of second root Frobenius norm. The summation is over rows and columns. So every element in the matrix, square that, sum them all, second root. And we denote it by F, standing for Frobenius. Okay. Xij denotes ijth element of X. Right? And you can see it as the length of matrix X. Someone in the previous course asked me, what is, so I understand, for example, L2 norm. What is the Frobenius norm geometrically? It means that consider a space of D1 by D2. D1 by D2 Euclidean space. You need to imagine it, you can't visualize it. Every point in that space is a matrix. The length of the vector connecting the origin of that space to that point is the Frobenius norm. Okay. Quadratic forms using norms. For X d-dimensional and X d1 by d2, you can write it this. So these are two important equations for norms. So these are quadratic forms. Second, so a squared L2 norm, you can write it as X transpose X. A squared Frobenius norm, you can write it as this. You will get rid of the second root because of the square. Also, because you can say, so the square is a Frobenius norm of X is equal to trace of X transpose X. And you can have more complicated things. For example, what is this? X minus Y transpose X minus Y. Right? Also, you can have the same for matrices. So you can see this as one thing and you follow this formula. So this is, as you see, this is quadratic. Why? Because of the squared, this quadratic form. And Quadratic format is like this, like a bowl. In 2D, for example, consider this is x1 squared plus x2 squared. When d is 2, this is like a bowl going up. If you take a look at it from above, it becomes like this. Each line means that the function value is the same. Okay. And derivatives. Okay. This is very interesting. Some of these were just roughly mentioned by Professor Botsi, but I really thought a lot about these things to understand it completely. So please come with me and we'll see the beauty of this. So consider when I say derivative of a scalar with respect to another scalar, what does it mean? What is the definition by definition of derivative? What do I mean? Derivative of something with respect to something else. What do I mean by that? Assume I say derivative of A with respect to B. Mathematically speaking, it means that tweak or change, modify B a bit. See how much it modifies A. How much the tweaking of B affects A. So now, high school derivative. Derivative of A with respect to B, A and B are both the scalars. Of course, the output is a scalar. Because whatever you do with B, it changes A. And that can be seen as a scalar thing. Now, derivative of A with respect to B, but let A be a scalar, B matrix. So A is a scalar, B is matrix. Sorry, vector. A is a scalar, B is a vector. D-dimensional vector. Okay. What is the dimensionality of derivative? D-dimensional. Why? No, don't take a look at that. So there you have a scalar. A is a scalar, B is a vector, B is a d-dimensional vector. Derivative of A with respect to B is also a d-dimensional vector. The reason is this. Each element of B you tweak, it affects A. How many elements do you have? D elements. How many effects for each of them? One effect, one impact. So in total, you have D derivatives. So it's derivative of a scalar with respect to d-dimensional vector is a d-dimensional vector. Derivative of a scale A, now A is a scalar, B is a matrix. D by N. Derivative is matrix D by N. Why? Again, with the same justification. Every element of this matrix you tweak, it affects that scalar. You have D by N elements. You have one impact for each of them. You can reshape them to be D by N vector, the derivative, but we usually don't reshape them. So we let the derivative be also a matrix. Okay. Derivative. Now A is a scalar, B is a yeah. I think it's good to say that it's okay. Let A is a. I think it's good. A is a vector. B is also vector. A is d-dimensional vector. B is n-dimensional vector. What is the derivative? A d-dimensional vector. B is n-dimensional vector. Derivative is a matrix, exactly. For each element of B, every element of A changes. What you consider tweaking one of the elements of B, it tweaks all of the elements of A. It has impact on all of the elements of A. Now go to the second element of B. It impacts all of the elements of A. How many cases do you have? You have B, N elements here, D elements there, D by N. D by N thing. Derivative, so now I think you understand that derivative of a scalar with respect to a scalar is a scalar. Derivative of a scalar with respect to a vector is a vector. Derivative of a scalar with respect to a matrix is a matrix. Derivative of a vector with respect to a vector is a matrix. Derivative of a vector with respect to a matrix. What is it? Sorry? Derivative of a vector with respect to a matrix. It's a three-dimensional. Three-dimensional. Right? You have two-dimensional for the matrix and one-dimensional for that. Derivative of a matrix with respect to another matrix. The four-tensor. Four-dimensional. Now I think you see the beauty of derivative. Now you can calculate the derivatives by justifying the dimensionality. For example, derivative of 2x, let x be a vector.
Cannot see the screen.
Sorry. Okay. Thank you. Whenever this happens, please let me know. So let x be a vector, a d-dimensional vector. Derivative of 2x, okay, with respect to x. If x was a scalar, output would be 2. Right?
Yeah.
And now the derivative of a vector. Wait a second. Let me say another example. Trace of. Yeah, I think this is a better example. Derivative of trace of x transpose x with respect to x. What is it? So trace of x transpose x is a scalar. With respect to a matrix, it should be a matrix with the same dimensionality as the matrix. So, and we know this is a quadratic form, x transpose x. So it must be something like 2x, like in a scalar, imitating the scalar. Didn't you enjoy it?
We need to get the
Okay,
version.
sure, great. Sorry about it. So we know that it should be something like 2x. Could it be 2x or 2x transpose? No, it should be 2x because it should be the same dimensionality as this. Now you see.
Would have to oppose it.
What?
Would have a different dimensionality.
Yeah, so it's a convention. I agree that either you should say that it's always the output is the same as dimensionality or transpose, but you should stick to it until the end. Okay, so using this technique, not only you understand derivative, but also you can calculate derivative easily for vectors and matrices by justifying the dimensionality, the compatibility of dimensionality and the multiplication of matrices. Right? I already explained it. Gradient and Hessian. Consider a function f. F goes from x to f of x. Okay. What is gradient? Another name for derivative, but for multidimensional. When we have your variable. Whenever your variable is a vector, usually the derivative is called gradient. But so it means that the gradient is usually a vector, because the f is usually a scalar, a function. And this is a vector, so the derivative is usually a vector. That's why gradient is usually a vector. Hessian, whenever gradient derivative is a matrix, they also call it Jacobian. Do I have it here? No, I have removed it. So whenever it is a derivative is a vector, it's usually gradient, otherwise it's Jacobian. Hessian is a second derivative. Okay, and it is a matrix usually. Why? Because f is usually a scalar the first derivative was a vector. The derivative of this first derivative with respect to the x again, it means that the derivative of a vector with respect to another vector, it becomes a matrix. Okay. So now Hessian, we understood that. Chain rule, I think you already know what chain rule is, right? Do you know everybody knows what chain rule is? Yeah. Okay, some examples here. The chain rule is important. Why? Because back propagation is nothing but gradient descent and chain rule. One slide about optimization. So consider minimization of f of x with respect to x subject to, we have some inequality constraints and equality constraints. Assume we have M1 inequality constraints and M2 equality constraint, right? I want to minimize this function, but I also want to satisfy these inequalities and equalities, right? I can write them in this way, the cost function, but I can penalize not satisfying the constraint. Soft penalty. So I can say that although I want to f to be minimized, I also want not satisfying the constraints to be minimized. I penalize them. This is called Lagrangian. For more information, you can see my course on optimization. This is called Lagrangian. You can write it in vector form too. And we usually in optimization, we can take derivative of Lagrangian with respect to variable and set it to 0. Similar to what we did in high school for finding the extremum of a function. We take derivative and set it to 0. Unconstrained optimization. That was for the constraint optimization. For unconstrained optimization, we assume, okay, when we have minimization of f of x with respect to x, what is the first thing which comes to your mind? What is the first thing which comes to you? Take derivative, set it to 0 in high school. But what if you do that and you can't find x in a closed form solution? So you take derivative, you set it to 0, and this is tangent of x over the second root of sine of x plus something very complicated. You can't find x closed form solution. Then what do you do to find the root of this equation? What do you do? Numerical analysis. What did you to find the root of a function? In numerical analysis, methods such as Newton-Raphson and these things, you do it iteratively in order to find. There are some techniques iterative. Yes. So the same idea is used here. When you take derivative, set it to 0. So the only difference is that in numerical analysis, you find the root of f. In numerical optimization, you find the root of gradient of f. Something like that. And if you do that if you use only first order derivative, it's gradient method or gradient descent. You go to the opposite direction of gradient. Assume you are on the mountain. You go in the direction which is up, because the direction of gradient goes to the mountain, to the top of the mountain. Minus gradient goes to the valley. All right. Newton's method uses both second order and first order optimization, both Hessian and gradient. For proof of this, you can see my course on optimization. We have proved, for example, Newton's method using Newton-Raphson. Simple. Constraint optimization, we can either use Lagrangian and these things, or we can use some methods such as interior points method, maximal method, these things. For more information, see that course. Eigenvalue problem. That's also important. Eigenvalue problem. Eigenvalue and generalized eigenvalue problems play important roles in different fields of science, including machine learning, physics, statistics, and mathematics. And all of them, it's related. It's very important. In the eigenvalue problem, the eigenvectors of a matrix represent the most important and informative directions of that matrix. This is a very golden sentence. So when you have a matrix, the eigenvectors of that matrix show the most important and informative directions of that matrix. For example, an example for you to understand what I mean. If the matrix is a covariance matrix, what are the most informative and important directions of the covariance matrix? The directions of the spread of data or variance of data, because covariance matrix is capturing the variance of data. So the most important directions are the directions where, for example, if we have a cloud of data points, the first eigenvector of covariance matrix is this. The direction of the spread of data. The second eigenvector is this. This is the second important variance, right? And this is exactly what we have PCA in machine learning. And the corresponding eigenvalues are magnitude of the spread in these directions. So eigenvalues are how much important in that direction it is. These directions are impacted by they can be impacted by another matrix in generalized eigenvalue problem. We'll see that. If the other matrix is the identity matrix, then that becomes an eigenvalue problem. Eigenvalue problem is this. I'll tell you what that means. This is defined as eigenvalue problem. A is a matrix. Phi I is a vector. Lambda I is a scalar. This is a matrix, vector, scalar. We have D of them. Why? Because the matrix is D by D. So we have D eigenvectors and D eigenvalues. Phi 1 to phi D, lambda 1 to lambda D. In matrix format, we can write it in this way. A phi equals phi lambda. Lambda phi has the phi 1 to phi D as its columns. This tags the eigenvectors column 1. Right? That's phi. Right. If you put the eigenvalues in the main diagonal, in a diagonal matrix, lambda becomes lambda. So lambda is a diagonal matrix whose diagonal elements are the eigenvalues. Okay. So that was the definition of eigenvalue problem. For the eigenvalue problem, the matrix A can be non-symmetric. If it is symmetric, its eigenvectors are orthogonal. Orthonormal. What does it mean? Two orthonormal vectors. It means that they are perpendicular to each other, and their lengths are 1. Each of them. If they are not symmetric, its eigenvectors are not orthogonal or orthonormal. Equation 7. You remember this was eigenvalue problem, right? Right multiply, because the direction of multiplication in matrices is important. Right multiply the sides by phi transpose. Okay. Phi transpose becomes 1 because it's orthogonal matrix. This is a property of orthogonal matrices. So we'll have A here. We'll have phi lambda phi transpose. As it is orthogonal matrix, you can write phi transpose as phi inverse 2. This is called eigenvalue decomposition. A equals phi lambda phi inverse or phi transpose. This is called eigenvalue decomposition, also called a spectral decomposition. Okay. Always we have phi transpose phi equals 1, I. So when you have phi, what when it is orthogonal matrix. What do I mean by orthogonal matrix? I already told you what orthonormal vectors mean. Orthogonal matrix, its columns are orthonormal. So when we say an orthogonal matrix, it means that the columns of that matrix are orthonormal. When we have this orthogonal matrix, if we don't truncate it, it means that if we have all of its columns, phi transpose phi and phi transpose are both identity matrix. If I take only a few of the columns, I truncate, I get rid of some of the columns. I always have phi transpose phi equals I, but phi transpose is not I anymore. An important thing. Okay. That's one thing. As I said, it's eigenvalue decomposition. The generalized eigenvalue problem is defined as this. If you see, if we set B to be identity matrix, it becomes an eigenvalue. The generalized eigenvalue. You can write it in the matrix format in this way. We write it in this way. Pair of AB. Phi and lambda are the generalized eigenvectors and eigenvalues of AB, and you can write this pair as they say it's eigenpair. Okay. One other thing, singular value decomposition. That's also important. I think this will be our last. So singular value decomposition, or SVD, is the most well-known and effective matrix decomposition methods. Whenever we say matrix decomposition, by the way, we mean that we have the matrix, we decompose it into the multiplication of several matrices. One of the decompositions was the eigenvalue decomposition, which we saw here, equation 8. You had a matrix A, you decompose it into the multiplication of phi, lambda, and phi inverse, right? That's why it's called eigenvalue decomposition. Singular value decomposition is this, is defined as this. You have a matrix A, alpha by beta. In eigenvalue decomposition, it's usually square matrix. In singular value decomposition, it doesn't necessarily need to be a square matrix. So it's alpha by beta. You can write it as U sigma V transpose, where U is alpha by alpha, V is beta by beta, sigma is alpha by beta. This is called complete SVD. I have complete SVD and incomplete SVD. As you see, sigma is a rectangular diagonal matrix. I mean this. We have diagonal elements and the rest is zero. Or this. Depending on whether alpha is greater than beta or less than beta. You understand it? Yes. This is complete SVD. Incomplete SVD, U is now, because in complete SVD, U and V were square matrices. Sigma was not a square. In incomplete SVD, U and V are not square matrices. Sigma is a square matrix. So U is alpha by K, V is beta by K, sigma is K by K. Now sigma becomes a square rectangular matrix. U and V in the singular value decomposition are orthogonal matrices. So we have these, and if we don't truncate them, we also have these two. So U transpose U and V transpose V are I. U transpose V transpose are I if we don't truncate them. The beauty is here. Beauty is here. There is a relation between SVD and EVD. Relation. So consider AA transpose. This is SVD of A. This is transpose of SVD of A, right? I can apply transpose to elements of these. When I apply, by the way, XY transpose is Y transpose X transpose. So it changes the order. That's why we have U sigma V transpose
here we'll have V sigma U transpose. V transpose becomes V. V transpose transpose is V. Sigma transpose is sigma. Why? Because sigma is diagonal. U becomes U transpose. By the way, here V transpose V is I. Because V was orthogonal. So we have this. Sigma sigma is sigma squared. We started from here. What is this? Eigenvalue decomposition. Do you see how beautiful it is? Question 8. Question 8. Recall this. So what? AA transpose. So we can say U, which was in SVD, the left matrix in the SVD, can be seen as the eigenvectors of AA transpose. U as in the SVD of A is eigenvectors of UU. Sigma can be seen as eigenvalues of AA transpose. Sigma squared, sorry, sigma squared. So it can be seen as a second root of eigenvalue. Consider A transpose A. I will finish it now. So it's like this. It becomes V sigma U transpose. U transpose U is I. We will have V sigma V transpose. So we'll have sigma squared. What does it? What again? This is eigenvalue decomposition. So in summary, consider SVD of A U sigma V transpose. U can be seen as eigenvectors of AA transpose. V can be seen as eigenvectors of A transpose A. Sigma can be seen as a second root of eigenvalues of either AA transpose or A transpose. This is the beauty. Okay, I think now it's good for this session. Then the next session will continue. I hope you enjoyed the course.
Thank you.